Wind energy is one of the cleanest of the sources of the renewable energy that we have available today, and one that can really help us tackle climate change. However, over the past decades, the size of wind turbine has increased considerably, leading to significant design challenges. This short video showcases 4 PhD projects undertaken at the University of Bristol under the Wind Blade Research Hub. These 4 research projects and the Research Hub aim to tackle wind turbine design challenges as a means to improve the cost efficiency of wind energy. Over to you, Matt.
Thanks, Terence. Rain droplets falling onto the surface of a spinning turbine blade cause the leading edge to erode, as you can see in the photograph. This is a major problem, as it affects the aerodynamic properties of the blade, ultimately leading to reduced energy output. Equally, it can affect the structural properties of the blade, leading to it being retired early before its expected lifetime. Testing these materials in the lab is very difficult because of the high strain rate impact caused by falling rain droplets. My work is looking at a digital chemistry model that can simulate the viscoelastic properties at high strain rates of polyurethane and other potential leading edge protection systems. Over to you, James.
Thanks, Matt. As wind turbine blades become longer, it becomes increasingly difficult to assess their dynamic behaviour. Linear stability theory can lead to dangerous predictions of instability and conceal nonlinear phenomena, ultimately leading to excessive vibration. Therefore, there is a need for nonlinear analysis tools. Using bifurcation theory, we can better quantify stability margins and more easily qualify non-classical instabilities. My work is using these tools to assess the sensitivity of parameters to the resulting aeroelastic response. For example, by introducing bend-twist coupling or geometric variations. Through this work, we aim to reduce the levelized cost of energy by improving highly flexible blade dynamics and consequently fatigue and ultimate loads. On to you, Sam.
Thanks, James. So, wind turbine blades are long, slender, wing-like structures that use aerofoils to generate lift. But given their slenderness, they also tend to be highly flexible and bend considerably under the force of the wind. Now, the aerodynamic forces that are generated depend on the shape of the blade as the wind flows over it. But the shape of the blade is also dependent on the forces. So what we have here is a coupling between the aerodynamics and the structural dynamics. And this coupling or phenomenon is known as aeroelasticity. Aeroelastic tailoring, on the other hand, is where you design the blade in such a fashion as to exploit the aeroelastic coupling for performance benefits. So these benefits might include passive load alleviation or improved energy yield. Now, my work aims to use what we call multi-disciplinary optimization, which is a mathematical technique often used by engineers, and we use this to design aeroelastic tailored blades. This technique enables us to produce innovative designs that reduce the cost of wind energy. So thank you very much for listening, and I'll hand you over to Alex.
Thanks, Sam. Additive manufacturing could significantly reduce the time and cost of wind blade production. Conventionally, wind blades are manufactured in 2 halves, where many layers of composite material are laid up into large, expensive molds, which often require replacement. 3D printing of internal molds to act as structural components as well as a layup surface could significantly reduce manufacturing cost and time due to automation and efficient use of material. My work involves the development of a design method for these 3D printed structures. I use topology optimization in combination with graded lattice architectures to maximize the structural efficiency within a design for additive manufacture framework. Back to you, Terence.
Thanks, Alex. If you are interested to learn more about the Wind Blade Research Hub activities, then you can directly contact me by emails or visit our webpage. Thank you.